Hello everyone, we are Kuvasz Rover team. My name is Máté Boda and I'm the leader of this team. We have team members from all over the country, including from Óbuda University, BME, students from Szeged and Pécs. This is a quite diverse team, not limited to a single institute. Instead, the common link is being mostly former CANSAT competitors. In high school, we designed tiny satellites for a national competition set out by ESA. There, we learned a lot about electronics, programming, teamwork and related fields. But now, starting university, and getting too old for CANSAT, we looked for new challenges. Having a common love for space and engineering, we became teammates from competitors to become part of a much larger project. The ERC seemed like a perfect place for us to put our theoretical studies from university into practice, learn about teamwork and how a real project works. Our main goal for this year is to establish ourselves, make connections and build a platform on which we can develop our future work.
The Kuvasz Rover team is led by team captain Máté Boda and vice captain Bálint Szegedi. To tackle the challenges, our team is structured into specialized departments. On the technical side, Máté Boda is responsible for our drive and control, Marcel Pál leads our robotic arm division, while Roland Gerendás is responsible for sensor fusion. For our operations, Bálint Szegedi is responsible for the management and Péter Árok leads the outreach. To ensure seamless workflow, we hold weekly stand-up meetings to synchronize our progress and handle all our management on GitHub. Together, these departments work in perfect synergy to bring our Mars rover to life.
This being our first year designing a rover, we had to make realistic goals and figure out what were some non-negotiable components and make sure we get those working. We chose an iterative and modular approach for our design. Iterative because it's a powerful method that works from smaller projects all the way up to the ones like SpaceX. Modular because for one, it ties in well with our iterative approach, but it also helps with testability, upgradability and maintainability. Our electrical design follows this mindset. We use a Raspberry Pi single-board computer as our main computer for heavy LiDAR and image processing, but most of our segments have their own individual microcontrollers. This way, critical hardware control is independent from our main software stack, and it also helps with upgradability and maintainability. We also built a custom LiDAR system. Commercial modules at our budget range either couldn't handle the ambient light we could encounter on the field or were very limited in features. We made a simulation to check whether one of the simpler ones would be sufficient. After confirming, we bought a module that couldn't even spin on its own. But designing a spinning mirror assembly above it, we ended up with a quite robust system. For the frame of our rover, we chose plywood. It's definitely not the best engineering material, but it's sufficient. And having access to a custom designed CNC router, we could manufacture designs in a single day, which really helped with our iterative approach. Our rover is equipped with a fully featured differential suspension system, 4 individually driven and steered wheels which allow for versatile navigation on rough terrain. We are using custom-designed geared hub motors for driving, closed-loop position feedback for steering, and a software-designed differential for speed control. For autonomous navigation, instead of relying on GPS, we are using an array of other sensors. At the core of our navigation stack, we have a constrained error state Kalman filter, or ESKF for short. This algorithm is the central state estimator software of our rover, seamlessly blending data from a bunch of sensors. An inertial measurement unit, or IMU, tracks linear acceleration, from which we can integrate speed and position, while the IMU and the magnetometer provides orientation data. A barometric pressure sensor provides us with altitude information. All of this is complemented by odometry, where a ground-facing camera tracks short-term displacement. By mathematically constraining the ESKF with the physical limits of a ground-based vehicle, drift could be significantly reduced. For absolute localization, triangulation is used from previously known artificial landmarks, while also being fully GNSS compatible as a fallback.